transformer, three-phase stuff today. And if you go, I think for the most part, we don't go over three-phase transformers, but I think it's important for you to at least understand the connections I had to some of the calculations. Very similar, really, to what we have done so far. But I just want to make sure you get that information as well. And then the other thing that I'm going to do today, I want to go over the open and short circuit test, how to perform it, how do you compute the parameters out of the results from the test that you do usually in a lab setting. And then next week, I really, really want to start getting to induction machines. So do 2 weeks induction machines and 2 weeks on synchronous machines. That gives us that pretty much takes us to the end. So any questions? I think I did a couple of examples last week, maybe one or two, right? Just on single phase. All right, so let's get started. So three-phase transformers. Three-phase transformers. Oh, one more thing. I was going to say, I might, depending on how the timing is, I might have to record an extra lecture for you, and you can watch it at your own time, depending on how we do it the next few weeks. So I don't want to forget to tell you that. So we say that three-phase transformers are widely used on transmissions, mostly on transmission systems. I'm going to put transmissions like substations. The way you can think of this, if you have a substation at the lowest voltage that you can possibly have, which is a distribution substation, I'm going to use this as an example. Say, for instance, and I'm going to use Edison as an example, but that can be PG&E, San Diego, can be any utility. Oftentimes they bring but in some companies they call sub-transmission, some companies they just call transmission. For instance, they can bring 66 kV, I'm going to use 66 as an example, and they have the step-down transformer from 66 to maybe 12, 16, 18 kilovolts, and then they bring feeders out of the substation to serve the different customers, right? So whereas here they might have single-phase transformers connected, which is the ones that we have discussed. They probably even the utility might have something, and the customer have their own single-phase transformers inside, right? Depending on what kind of loads they're serving and what voltages they. These transformers, as I said, all the feeders is what we've been discussing for the most part. Like they're single-phase, maybe two-phase transformers. Now the substation itself, and then beyond, if you get into higher and higher voltages, these are almost, I say, 99% of the time three-phase transformers. So they're widely, as I said, used on transmission system substation applications. We say that similar to single-phase transformers, and we talked about this already. Three-phase have very high efficiencies. So in other words, we have very low losses as well. This transformers could be very heavy due to the large core mostly, and we can say coil, but really the weight comes from the core of the transformer, of the steel part of the transformer. But they tend to be more than distribution transformers, very, very heavy in nature. Um, we said that in most cases, um, three-phase transformers are, I want to say in the most cases, but maybe almost 99% is very rare, probably like 1% that are not oil cooled. So these are transformers that are oil cooled transformers with radiators, and we talked about this already, and in some cases fans. um, Three-phase transformers to be Y or delta connected. And we'll talk about this just in a bit. So then they can be Y or delta connected, they can be YY, they can be Y delta, they can be delta Y, they can be delta delta. So there's all with the Y and the deltas you can make different connections depending on the application, depending on the design of this transmission system. That's basically what we do. Three-phase transformers could be a single piece of equipment, one box, I'm gonna say, and we talk about this too, or three, I'm gonna say three pieces to make what we call a bank, transformer bank. Okay, and remember we talked about this, the radiators and the fans, and that depends on the rating of the transformer or how much juice you want to get out of it. With no radiators or with no oil moving, you can get so much power out of it. You can increase the power output of the transformer by turning on the radiators and fans. And most important, if you want to add, you can also add, I forgot this one, a pump, and I mentioned this, to further increase. So you can use radiators with fans and a pump to increase the capacity. And that has to do with the materials, right, of the core especially, because that's where you incur most of the losses, the type of windings. As a matter of fact, we were discussing this last week with a transformer manufacturer, an Edison, and this company now says we can get transformation, very high transformation in MVA wise, without the need for radiators, fans, or pumps, which obviously is their trademark. That's one thing that they're starting to advertise, saying, hey, we don't need all those equipment to get more juice out of the same box that you otherwise will have to add that. And obviously, those are trade secrets. They don't tell you how they do it. The only thing they tell you is, oh, by the way, we're using different type of materials now for the core. So the losses are very, very low. But I say right now, 95% of the time, you're gonna need some of this, okay? Utilities will be skeptical about those kind of things because those are new type of designs and they're very conservative as far as how transformers are designed. So I don't know, but it seems like transformer companies are starting to move into that space where they might not need moving parts. which will be a great thing, but especially for maintenance, but it takes time to catch up. Um, let's see. So the power equations for three phase and how you deal with transformers and how you do computations, very much what we've already discussed, right? For real, reactive, and apparent power, I'm just gonna rewrite them here so that you have fresh in case we need. So power formula for three-phase R, P equals square root of 3 V line to line I line cosine theta, and theta being the voltage between the voltage and the current, as we have discussed it, and J, Q is square root of 3 V line to line, and this is magnitude, remember, not phasors. Magnitude I line, sine theta, and this is a J right here because that's your imaginary part, and then S for a three-phase transformer is equal to square root of 3 trans D line to line, this is a phasor, times I line phasor conjugate, right? So the formula is nothing new. We have already reviewed those previously. So, for instance, if you were to have a delta, one side of the transformer, I'm going to call this the primary, as a delta, this is what we call the I line. This is the voltage line to line from A, B to C. So that's what we call line to line. And we talked about this before, where in this case there is no neutral, right? So we only have line to line. And then we have what we call the phase current. If you hear word phase current, they're referring to the current entering this from the line here to the line here, meaning from point A, in this case to be from A to B, current B to C and C to A. And then on the secondary side, you can have the transformer as a Y connection like this, with the neutral. I'm going to put the neutral there, or maybe I'll put it in here. And then I'm going to have this right here. Okay, so in this case, on the secondary side, we have I line, and in A, B, C. Actually, I should have put them the other way, but you have A, B, C, and then you have the secondary winding. The I line is the only thing you have here. So in some cases, you might see it when they tell you, oh, this is the I line to the point where the transformer is actually winding is connected. And then right after that, even though it's the same current, they might call it I phase. So in a Y configuration, you can say that I line is equal to I phase. And then in this case, we have a neutral point right here. So we have B line to line, and then B line to neutrals. And I think we talked about this already, where you have 3 currents and 6 voltages. In this case, you have 6 currents and 3 voltages that you're dealing with, right? So same thing that when we were talking about three phases. But now we're connecting, obviously, transformers. Okay. The voltage relationships for the windings, so you can have, again, the Y configuration. So you have these 3 windings on a core, of course. And this is your, once again, your A winding, your B winding, actually your B, I'm going to put it here. B right here, and then last but not least, your C winding, B plus, minus, and then plus, minus right here. And this right here, once again, we said that they're starting with A. We can start with A. A is at 0 degrees. B is at 120 degrees, and then C is, minus 120, and C is at 120 degrees. And I think we talked a little bit about that as well before, but we'll get into some little more details. On the delta winding, on the delta connection, you have the windings of the transformers connected in this way, where we can have A, B, and C. And you can use the C to A or A to C as the reference, or the A to B or the B to C. But in this case, you can say this, I'm gonna put it at 0 degrees. So this one, the A to B will be at 120 degrees. And you can have this C to B to 240 or minus 120 degrees. We'll talk in more details on that, but that's basically your transformer voltage or winding relationships that we have. Okay, so, and this is the one thing that I've discussed before when we're talking about very large transformers, in which you probably will have 3 single-phase transformers, separate boxes, I'm gonna say, and then you can connect this together any way you want. And by the way, don't large transformers, I think I did mention to you guys, hey, what if you have a customer on your distribution system, right, that requires, like Capoli Pomona would be a good example. Capoli Pomona, most likely for this buildings, require a 3-phase voltage source from the utility. So rather than using the single phase from the pole, they bring either a pad-mounted 3-phase transformer somewhere outside this building, or they probably have 3 transformers, single-phase, pole-mounted, connected in either YY, delta delta, whatever the application might be. So let's think of this as an example. I have phase A, phase B, and phase C. So I'm going to say A, B, and C. We're going to say this is for the source line. And then on the other side, we're going to have this bus, A, B, C. Okay, I'm going to say this is the low side. And then I'm going to add here a neutral conductor. Okay, so this is the load, and this is the source side. Okay, now you can take 3, once again, single phase transformers. In 3 separate boxes, as an example. And you can, with 3 single-phase transformer, you can build any type of connections that you want. In this case, we're going to say this is going to be a delta on this side, or on the source side, delta, or the primary in this case. And then Y, I'm going to say Y grounded on the secondary. So this is Y, this is delta, and then I'm going to say Y grounded, because it does matter. Okay, so basically what we're going to do, we're going to have this as the AP input, BC, and then CA right here. So obviously all we do is we connect to phase A right here, and phase B on the wires, right, of the source side, and then B and C go to B, go to C, and last but not least, we have from C to A wire. And then these 2 lines, by the way, if you see 2 lines, I think I mentioned this before, this means that the transformer is this galvanic isolated or not physically but magnetically coupled. That means that there is no connection between this winding and this winding. The only way we can transfer, again, energy from this primary to secondary is through the magnetic field. And we talked about that. So on the secondary side, we have this connection. This is going to be A to neutral. So connect this to neutral. This one is going to be from B to neutral. And the last but not least will be your C to neutral. So this is B to neutral, and last but not least C to neutral. And I say this is grounded right here. So the neutral on the secondary is reference, is connected to Earth. I'm not gonna get into the details of this, okay? But I just want you to remember, if you're ever asked, or if you ever have to deal with this kind of connection, especially if you're on this side of the transformer, and here's where you're gonna feed your loads from a wide grounded system. Um, you can, the only place where you can do this connection between the white, this is usually a white wire, white, and the green wire, which is the ground, is here. From here, you're gonna feed loads, right? It can be that panel that is being fed from a transformer, and you can no longer take the neutral and the ground of this transformer and connect them together. In other words, let me say this. Say you have a load right here. I'm gonna put it as a resistive load, in resistive inductive load, okay? And this one comes to neutral. Say you're doing phase to neutral, and then I'm gonna take this phase, C phase, and feed the load from C to neutral, okay? You can think of this as a box. It can be this panel right here. It can be this bench right here, if it's been fitted. If you go to the lab, you'll see it. If you're in the lab with me in this semester or with somebody else, you'll notice we have the boxes, the benches will have a green wire going to ground, okay? You have a green wire going to ground. Here, as I said, you can do this on a white grounded system, a white grounded transformer. You can bring the neutral and connect it to the reference at this point. However, once you go feed all your flows from a three-phase white grounded transformer, you can no longer take this neutral wire and connect it to ground. That's a safety violation. That becomes a big issue. Is that something that people keep track? In some cases, they don't, and it depends who's managing the building. Yes, sir.
That load is still an AC load, though. You're still taking a switch.
That is true. That is true. Still an AC load. Still an AC load. The issue here is safety violation. Is it because somebody, for whatever reason, this connection is made, you can actually become also back to ground for current from the chassis, so from the metallic part of the load, right? The box, the case, whatever is enclosed. So this right here is a violation. And why will people do that? And by the way, it's not really uncommon. You'll see it as you come, I mean, if you work for utilities, you don't deal with this side. You mostly you stop right here and you let the customer do whatever they want once they go in there. So utilities engineers don't often have to see this. But if you are a facilities engineer for a, I don't know, factory, refinery, whatever that might be, you will come across these cases. And the reason being, once again, is because sometimes this neutral right here coming here was supposed to be zero reference, right? Very tight. And sometimes what happened is that they develop some voltage right here and there's no longer, this point right here is no longer grounded or zero, okay? So it's very easy for somebody to say, and I don't want to bash on technicians, by the way, because you have to work with them and they know their stuff too. But somebody comes and complains and says, hey, my reference, my neutral, my face-to-face voltages is not as good. It seems like my neutral is bad. I don't have a good solid neutral. So they measure right between the neutral and the cabinet, and they said there is a voltage. Oh, they need grounded, so I bring everything to zero. You cannot do that. So that's one thing that I want you to just keep in mind if it comes across. If you go, there is a book that we follow. It's on the secondary side, on the low side, on the customer side, which is called the NEC, National Electric Code. They talk about this in more details. But like I said, that's one hint that I want to give you because it does come. And if you deal with this type of transformer, especially white grounded, it might come. Okay, so if here's something, and you may say it's a disadvantage. I don't see as much as disadvantage as a fact. So if I take the phasor for voltage A, B, I'm gonna take this as the reference, meaning this voltage right here. Okay, I'm gonna say that's my reference. So if and I'm coupling, you see basically what I'm coupling is this winding, it's coupled to this winding, right? But here I made it A to neutral, right? Because I made a Y out of this. So the line, using this A to B as the reference, meaning voltage A to B, magnitude angle 0 degrees, my line to neutral voltage on the phase that I've been coupling, in this case A to neutral, is going to be obviously I'm stepping down, so magnitude will be smaller, and this will be V A to neutral is equal to V A to neutral magnitude with an angle of, in this case, will be 30 degrees, so you can say minus 30 degrees. So this 30-degree shift between these 2 points, phasor, and these 2 points, phasor, okay, always 30-degree shift. Another way to see it, and if you come across transformers, especially delta white grounded transformer nameplates, they probably have something like this on the nameplate. And this is, I'm going to say again, A to B, B to C, C to A, and then you'll find this. Okay, and they're going to call this one B, they're going to call this one A, and they're going to call this one C. So meaning this, they make you have a triangle right here representing the delta side, and then you take these phasors and then bring all of these arrows to the center, and you make A to neutral, B to neutral, and C to neutral. So we call the center of that the neutral point of the transformer. And like I say, you'll see that, especially when if the transformer is being designed as a three-phase transformer on the nameplate, you'll see this marking, or on the one-line diagrams that they give you for that transformer. Yes, sir.
So is this system used to transmit over long distances and then give loads like?
No, these transformers, and good question. For the most part, let me see.
Like, what is this used for?
Yeah. Edison, I'm going to use Edison as an example. Okay, Southern California Edison has three. They call A systems, and B systems. Okay, the 8A are substations that transform voltages from 500 to 230 kilovolts. The A are stations that transform from 230 to either 69, 66, or 115 kilovolts. And the B stations are the ones that convert 69, 66, 69, I'm going to use 69 or 66 or 115 to 12, 18, 12, 16, and 18 for not that many kilovolts. So they call this double A station, they call this A stations and B station. How does that come into play here? Okay, this is how it is. So you have an A station. I'm going to use the maximum number of transformers that they will have. They're all three phases, by the way. Okay? So this is what we call a double A station. Okay? 500 on this side, 230 on this side. These are wide grounded transformers. Okay? So that's a substation. That's a facility, right? From here, they obviously connect these transformers like this to this bus. They make a bus. Here's what the source is, right? here's the source, the generation, I'm gonna say for now. From here, then they have lines. They have a line from here, and this line obviously is 230 kilovolts, and they go to an A station. So an A station is fed on the primary to 30. Here's another 4 transformers. Maximum capacity for Edison substations, and PG&E I think is the same. There's 4 transformers per substation. So here's the other substation. Do you follow me so far? Generate is coming from the 500. They have a 500 kV network, very large network, where all of the generation is being connected, or most of the generation. They have to bring it to, say, the city, right? So they use this substation with transformers like this to connect it wide. Okay? That's the lines that you see, the transmission lines that you see outside. So those are the transmission lines. So they might bring 2 transmission lines to the substation. This is a location, this is a substation. And they might have another, I'm gonna actually do it this way, another substation right here.
So in that double A, that would be the equivalent to what your Y ground network is with ABC neutral.
That's the next thing that I want to talk about. My station right here is going to be white grounded.
Which
no
is,
delta. There's no delta.
Yeah, but it's like that Y ground that you have, right?
Correct.
Okay.
Correct. So now from that substation, this substation says this substation has a capacity of, I'm going to take a number, 1,000 MVA, right? So far so good. So I have 1,000 MVA of transformation, and there's 3-phase transformers, white grounded on the primary and secondary, meaning white grounded on 500, white grounded on secondary. From there, you're going to feed a bunch of other stations, okay, which Edison would call A stations, okay? Maybe this transformation is, we said 1,000. Let's break that into 250 MVA, okay? So from here, you can feed 4 substations. From here, you're going to feed the smaller substations, right? Also for transformers, but they're smaller in capacity. And then from here, you're going to have your distribution feeders, okay? Do I make sense?
Sort of.
Well, you'll review this on the transmission line class. That's what they're going to teach you.
It's kind of like the house main breaker has 100 amp, we split it into 50 amp.
Correct.
5 amp.
Basically, that is what it is. You have, the utilities will have this very large substation that can handle 1,000 MVA. But as you get to the customer, that's a lot of energy. So then you start splitting it. The way you can think of it, this is the city of, I'm going to use Chino Hills.
I was going to say that the stepping down is not the confusing part for me. The confusing part is what's the benefit of a Y network versus a delta in this.
Oh, we'll get to that. We'll get to that.
So like,
We'll get to that.
Like what makes it the decision to select Y?
Yes, we'll get to that. So you understand that though,
Yeah,
right?
yeah.
Basically, what they're doing is they're just splitting it, right?
Yeah, a distribution.
So they become smaller and smaller and smaller, so till you get to this distribution transformers that are single phase,
Right.
25 kVA, right?
Right.
Makes it, okay. By the way, you learn how these are connected on the transmission class. Now, what are the advantages? Before even talking about this, there's advantages and disadvantages to this, and why the utilities do it, right? This delta Y transformation and the 30-degree shift is a disadvantage, because you always have to remember that when you're connecting systems on the secondary, there's going to be this 30-degree shift that I just mentioned here. VAB and VA to neutral 30-degree shift is always going to be there because of that delta Y transformation and the way the windings are connected. So you can say one of the disadvantages is 30-degree shift between primary and secondary. Okay? An advantage is that the delta winding provides with isolation to third order harmonics. That's a big advantage of delta Y or Y delta when you have this transformation, because what happened is, say for instance, you have customers right here who happen to have, lots of nonlinear load, and they actually require third harmonics to function. This side will see the third harmonics, but when you get to the source, the third harmonics get trapped into the delta, into this delta. They circulate, but they never reflect back to the source. That's one big advantage of delta Y advantage, and I consider that disadvantage. Yes,
When you say third order harmonics, you're talking about like switching loads that affect the source, right?
correct. If you have this kind of loads, right? I'm gonna say non-linear loads can be at least a charger, right? It's a good example, like a battery charger for either vehicles or batteries, right? Or if you have a solar PV plant, you have a rectifier, so you have what we call non-linear loads, right? Because they do not consume current like this, but most likely something like this, right? So they're non-linear loads, right? The advantage is that this waveform, obviously not being non-linear, this waveform right here, this side sees it, right? Because this has fundamental and third harmonics. And harmonics, I'm gonna say, not just third harmonics, but the third harmonics, they get trapped on the delta and they don't get reflected to your source. So that's a big advantage of this type of transformers. You guys will hear it, not the utilities, but the industrial people, they call some of these transformers are called K-rated transformers, meaning, oh yeah, they will specify K-rated. And the reason why they do that is because they say, hey, I want a transformer, right? I don't know, I'm gonna say 12 kV on the primary to 240, 120 on the secondary, three phase, so 240, 480, 277 on the secondary for my loads. So when they specify it, they will say, and I want that transformer to be K-rated. You'll hear that term, and a lot of times people don't even explain it. What is K-rated? Well, it can handle more energy. It's a beefier. It has more wire than a conventional transformer. And the reason being what they do that is because now you're having to deal with this currents beyond the 60 hertz and their currents. So you still have to deal with the I-square losses. So they oversize the windings of the transformer, the core of the transformer, to handle more power, or because they're gonna have to deal with higher losses because of the type of loads that you're dealing with here. But again, if you want to get into more details, and if you are working in industrial systems, you'll hear that terminology. That's really what they mean. Point I'm trying to make is that if you have if you have a delta, whether it's on this side, you have the ability to drop those third harmonics, but just third. So if you have a 7, goes through. Yes, sir.
So in reality, or in real life, the power plant would have a delta wire, and they will go to the transmission line as Y ground.
Say that again.
So from the source,
Yeah.
is the power plant.
Yeah.
It will be it start with a delta.
Yeah.
And then immediately when you go transmission, you just convert it into Y ground all the way to your house.
As I said, remember when I was explaining this, I said it depends. On 500 kV transmission lines, you don't have that.
Okay.
Right? There's no neutral. It doesn't exist. Neutral is earth. That's the path back to the source, and only for faulted purposes. So they might have a transformer like this, but they don't actually have a physical wire. If you look at transmission towers, right? If you go outside and look at distribution, transmission towers, you'll see 3 wires. There's sometimes a wire right on the top, and people always get confused. Right away, people go and say, oh, that's the neutral wire of the transmission line. That is not the neutral wire. That is a non-carrying conductor. That is, only purpose of that is for lightning protection. Because you have a very high structure, right? And it's metallic. You have a cloud charge right here. What is the cloud? What is the discharge gonna go? To the path
Of these.
least resistance to ground. Right? So that's the reason why. I mean, when you see tall buildings, you see that little antenna, right? Which is basically that's what it is. Is to make sure that if there's a lightning discharge, it doesn't hit the structure, but it hits that and it grounded. Same thing with transmission. Okay? Even if I say, oh yeah, the 500 kV system is a wide grounded at the substation, but you don't build a neutral. You don't take this wire like this on the 500 side. The line only has this A, B, C wires. This right here is grounded, but it's never used. You don't use that because you're not connecting those on the 500. Do I make sense?
Yeah.
Where you start needing grounds is once you get to the customer. That's when you start needing grounds. There's so many variations of this. I don't want to overwhelm you. Like if you go work for Edison, Edison might have distribution, DWP is known for that. Their distribution system is Delta. And there's some disadvantage, and we'll talk about the disadvantages of the Delta side. But it's more reliable. It happens to be more reliable. But they have a lot of issues protecting because they don't have a ground, they don't have a way to monitor current right here. There's a lot of disadvantages, right? But you still have that. The other, so this is your Y configuration, so the advantages and disadvantages. Okay? Let me keep that 30-degree shift. So you cannot, okay, the other type of connection you can have, and then you can combine them, by the way. We'll talk about that in a bit. You can also have a transformer that is delta on the primary and delta on the secondary. Or you can have, like I said, a transformer that is Y-Y. Let's do this one. So you can have phases, once again, A, B, and C, right here, and a neutral, okay? And then you have on this side, same thing, A, B, C, and neutral. I'm gonna make this lowercase, A, B, and a small c right here. So I have my wires inside the substation. I'm gonna say this is a substation, that's what the transformer is. And then you have, again, 3 transformers. I'm gonna make them separate, single phase. Okay, single phase. And then we do the same thing here. A to neutral, B to neutral, and lastly C to neutral. On this side, we gotta do the same thing. A to neutral, B to neutral, and then last one is C to neutral. So this is a Y, I'm sorry. And then you can run both ends, but I'm gonna say Y for now. This is Y on the primary, Y on the secondary. When it comes to the phasor voltages, let's use A as your reference. B, A to neutral, meaning on the high side, A to neutral. And when you go to the secondary side, your lower or your low side of the transformer or secondary is A to neutral. Might be different magnitude. You're gonna step it down. This is the A to neutral. They happen to be in phase. Okay, so you have no phase shift on here. Now, back to what I said, advantages and disadvantages. Okay, the advantage here is that you have no phase shift. Okay, and like I said, I'm pretty sure when you take the transmission line course, they're gonna go in more details on that, right? But beyond the transformer. But one of the that's one of the advantages, right? That you don't have to think about phase shift. You don't have to deal with that, right? Especially when you're trying to connect two systems that are in parallel. If one happens to be delta, the other has to be Y. You cannot do that, right? So that's I'm gonna say a big advantage. So I'm gonna say advantage is that there is no phase shift between primary and secondary. Disadvantage is that third harmonics do get reflected to the primary side. Again, you're gonna connect your customers, or you have your loads, I'm gonna say your customer, your loads on the secondary side, and if you have, again, nonlinear loads that produce odd harmonics, within those odd harmonics, you have third harmonics, they're gonna be reflected to that side. So this source side is going to see those harmonics as well. Obviously, one of the challenges still is in the industry that the loads themselves should be designed to produce there's a limit on the amount of total harmonic distortion they should have. But everybody checks? Not necessarily. The other thing is all of the rules that we have in place, right? When we have loads connected, meaning nonlinear loads, are for loads that are maybe, I'm gonna think of educating is 10% of your loads on a distribution system are nonlinear, right? Well, that's not the case anymore because as you start adding battery chargers, solar PV, electric vehicle chargers, those third harmonics or even harmonics continue to increase. And in many cases, this transformer had not necessarily been designed for that. Because as I said, you're adding, the transformer is being designed for this, a 60 hertz waveform. But as I said, these nonlinear loads are producing, say, third harmonics is really high, right? So 120 hertz. So you're gonna have 120 hertz on top of the 60 hertz. This is a current. You still have to deal with a current, right? So that's one of the disadvantages. But as I said, I'm getting too much into the details. The important thing is that you can take 3 single-phase transformers and connect it any way you want. You can make it Y, you can make it delta Y, you can make it Y delta, or if the transformer is designed from the get-go, sometimes they just design it as you specify. Now, here's the other thing I was gonna say. If you have, I'm gonna extend it just a little more. If you could have a system like this with the 3 phases, A, B, and a neutral from the substation, I'm gonna say, you can also do this. Nothing wrong with this. You can take another set of transformers right here, okay, and connect them this way. A to B, B to C, and then C to A. And you can do the same thing here. You can make this a delta like this, and A to B, B to C, and C to A. Meaning from the same line, you can connect whatever the 3-phase transformers in whatever combination you want. You're not restricted to that. Okay? That's why. And why? Now let's go back to this side right here, the delta. And I mentioned advantages and disadvantages. let me go to the secondary side. So you have a delta here, and here are your loads. Here's a load, here's a load, here's a load, okay? I'm talking about this load connected here. And this is A, this is B, and this is C. Here's an advantage of a delta connection on this side. Say, for instance, you lose this connection, okay? You lose that connection. You can still get to that load. You still get to this load. You still get to this load. You have an imbalance, but you still can supply the load. You see what I'm saying? Okay? So that's a big advantage of a delta connection. That's what I said. I'm not saying exactly that's why LADWP, as an example, decided to have their distribution systems to be delta. But I will probably make that argument that probably to them, the reliability was really important, right? So if they lose one phase, they still can serve their customers, not permanently, but they can still run the loads while they fix the problem, but they never lost a group of customers, say on this leg right here. Now, if you have a Y connection, I told you some of the advantages of the Y, especially for protection. I don't want to get too much into it, but protection, people like this connection, this ground, neutral to ground, because they put a device here to monitor current, and when they see an imbalance, they assume it's a fault. I'm not gonna, like I said, I'm not gonna get too much into it, but here's the disadvantage. If these are customers or loads, you have A, B, C, okay? If you lose this wire right here, you cannot get to this customer, right? Current comes here, oh, there is an open. Current comes here, oh, there is an open right here. So basically, this right here is not as reliable as that, okay? But the biggest advantage, as I said, biggest advantage is that you have this connection, and when you have this open, the imbalanced current will flow through that, and that is good for protection engineers. So, is there it depends on the type of the loads that you're going to be feeding. The other one the other type of loads that engineers, right, especially facility engineers, like to feed is as a delta is motors. Because if you feed motors with a delta, you can lose one phase, but you can still run your machines, right? There's going to be some issues, obviously, overloading on the lines because it's an imbalance, but you can continue, the process, whatever process that they have, and they can come back and fix it without having to lose the motors, right? So motor loads are known, and I'm not saying 100%, but they're known for being connected delta as for the fact that you have that reliability. I don't think we do any all of the labs that we do on the machines, we use the Y connections. And the other thing I think why Dennis was the one who created all the labs did it is because it's a lot safer to do the Y connections than the delta connections. So if those of you who are in the lab with me, you've seen it, right? All of the connections, we have always, all the machines we have connected, or we have fed them with a delta connection or with a Y connection or with that delta connection. But when you're in the lab, we can discuss in more details. What I'm trying to make once again is that you can have any combination you want.
Just to clarify, on that delta connection, for example, those rectangles, that would be the load in case you're talking about a motor, right? But in the case you're using transformers, your transformer could go in those places as well, right?
That is correct.
Right. Okay.
Yeah, that is correct. That is correct. So, like I said, once again, I'm gonna say this. If you go work for Edison, unless you're field engineering, you come across this kind of stuff and this kind of connections, but not to the level of details. If you work for a consultant maybe, or if you work for facilities, especially factories, this comes a lot. This is gonna come a lot to you. But once again, the point I'm trying to make is that you can make any type of combinations with three-phase transformers. You can make Y-Ys, you can make Y-delta, you can make delta-Y, and then you come across some other really funny-looking ones. There's an open delta connection. Transformers, you can say you don't have a lot of money, but you say, hey, I'm limited on the money. I have two transformers, and I have single phase loads that I want to feed. From this, you hear the word open delta, meaning you only have two transformers, so you can make an open delta with two transformers and still feed loads, right? There is another one called Y, where you have the winding right here, the winding on delta winding right here. You can have a split delta, meaning you can have voltages from the middle of the winding to this line, from the middle of the windings to this line. Scott connection, there's just so many.
Is that how
So
you
many.
get two different 120 in the house?
How you get to 120, and I did that example, and I'll give you that example as a homework, as a matter of fact. I'm gonna post the homework. But let me answer that question. So does this right here, three-phase transformers, is for large customers, right? I'm gonna say large customers now. Where you want three-phase transformation because the customer has three-phase loads. But you can also have this. Here's the source line of the utility. I'm gonna say the utility. You can have a transformer connected like this, just a single phase transformer, which is what I did at the very beginning. And I'm gonna say this is A to B. I'm gonna say this is the secondary of the transformer, right here in the primary, between these 2 points. I'm gonna say this is 12 kilovolts line to line. So this is voltage line to line. On the secondary of the transformers, those are the ones that you see on the poles, right? Single phase transformer. Basically what you do, you split this into two, in half, and then you make this, you can say this is the center point. And between these two wires, you have 120 volts. Between these two, you have 120 volts, which is what you have here. So the plugs right here, outside to the transformer, if it's a single phase transformer, some of them are fed from this side of the transformer. Some of them are fed from this side of the transformer. In the lab, we have 208. That's the voltage that we have in there. Okay, so how do we feed, 240. How do we feed 240? Basically what we do is then you take this 240 from this point to this point. So you're using a single phase transformer to provide you with two voltages, two 120s, and you can connect loads to this, right? You can connect loads right here like this. I'm gonna save this plugs right here. And then you can connect a set of other plugs in the same building from this center. Here's my other plugs, here's my other plugs, here's my other plugs. Or you can actually say, oh no, I have a 240 volts load right here. Okay, in some cases you need 240 volts, right? Typical 240 load is your washer, and you've seen the plug in the washer, right? It's something, or your dryer. It doesn't look like 120 volt plug, right? It looks like, yeah, it's a prong, right? So that's most likely a 240. Physically, as I said, on the transformer, this is a single phase transformer, and I think I gave you the picture. If you remember, we had a picture and it looked like this. Here's and then you'll see it outside. Here's the insulator. Basically, that's what it was. Connected to A and B. And then here, you'll see this things right here. This is called X0, X1, and X2. Okay, well here, what it is, between these two is 120, 120. So you feed your single phase 120 loads, and then you can feed, people call this single phase loads, but they're not necessarily single phase. I mean, in reality, these are two phase loads. But we call it single phase 240. Do I make sense, everybody? Okay. I'll give, as a matter of fact, like I said, there's on the homework, there's an example like this, and that I want you to work through. as this one. I do one three-phase. Okay, so Y delta, delta Y. You covered this in a lot more details for your transmission line class. I think that's the next one that you take with transmission lines, or
I think it's an elective.
what, say it again?
It's an elective.
Oh, it's an elective?
Yeah, so we have to choose that class to take.
So, remind me, there's transmission lines, and what's the other one that you have?
I think it's advanced power systems, or just power systems engineering.
Is that what they call it?
I'm not sure.
Okay,
Yeah.
so, I mean, if you're serious about power, I will take those classes, because Sean will probably go into more details on that. The idea here is I just wanted to introduce you to three-phase transformers, so when he starts talking about it, take his class, at least, but he's gonna go into more details, how they're connected, how is the system transmission, especially, design and all that. So I just want to give you a little bit of that, so when you go to him here, if you take it, and like I said, if you're serious about power systems, I'll take those electives. Somebody was asking me last week, as a matter of fact, I'm glad you guys brought that up. Should I take power system analysis as an elective, or should I take power electronics? My recommendation is that if you only have the choice to take one and not both, take power system analysis or transmission lines. Leave the power electronics for later, because those are that to me is the next logical class in power system. There's a lot of things that you cover here that obviously we don't do here, such as low flow analysis, maybe data about protection, a little bit about stability and all that, transmission line parameters and all that. So that would be my recommendation. But if this is just an elective and you're not interested in power, then I don't know. It's up to you. Any questions? Okay, so let's do this. Let's do a quick example. God, I need a better eraser. Okay. Let's see, example. A three-phase transformer has 500 turns in the primary and 50 turns on the secondary. On secondary. We say that if the transformer supplies also if the transformer is supplied by a 2.4 kV source, find the secondary voltage if the transformer is connected Y delta, we find the secondary voltage if transformer is connected as delta Y. So two type connections, Y delta and delta Y. So let's start with A. So A, we're, once again, they're telling us that we're gonna connect it, like this. Y, primary winding, and then coupled with the secondary winding like this. Like this. This winding right here, you can see, you can think of this way. This winding is coupled with this winding. This winding is coupled with this winding, and this winding is coupled with this winding. So, so it's as I said, it's a Y delta. So N1 is equal to 500 turns, and N2 is equal to 50 turns. Okay, and we know what they give us is that on the primary side, the voltage line to line is equal to 2,400 volts, right, or 2.4 kilovolts. So that's on the source side. So we know that. Okay, basically what they're telling us is this: K on this delta, the line to line is 2,400 volts. Okay, so we know that. We know that the line to neutral voltages on this side. So therefore, we know the voltage line to neutral, and I'm talking about primary. Let me write it right here so we know that. Is equal to V line to line divided by square root of 3. So that gives us 2,400 volts divided by square root of 3. So the voltage line to neutral on this side, or the Y side, is equal to 1,385.6 I have volt. Okay? So once again, if you apply 2,400 volts between A and B, you're gonna get 1,385 volts between A and neutral. That's basically what we have. And I'm once again, I'm coupling this with this, this with this, and this with that. Okay? So then I can say that V2, which is on the secondary side, I'm gonna put this line right here. I said that V2, and I think you guys have those formulas already from the single phase transformers, but V2 is equal to V1 times N1 divided by N2. So in this case, we say that this is equal to 1,385.6 volts times the turns ratio, which is 50 to 500, right? That's our N2. I'm sorry, that's our N1. Did I do this wrong? Oh, I'm sorry, this is N2. N2 over N1. I'm sorry, correct that. So that's 50. So that gives us the voltage V2 of 138.56 volts. Okay, where? Well, as I said, this right here, this is coupled with this. So this 138 volts is the line-to-line voltage because it's a delta, right? Do I make sense, everybody? Okay, so that's my V2 right here. So if we want to write this, we can draw it this way. Here's my transformer. Three-phase. Okay, I'm gonna say this. And here's my delta side. Three-phase, of course. So what I have is the following. I have once again between the line and line, and this is A, I'm gonna call this B, and this C, and this right here a neutral wire. Okay, B. So V, A to B magnitude is equal to 2,400 volts, okay? And V to neutral magnitude only, in this case is 1,385.6 volts, okay? Now I go to my secondary side, I only have to deal with one with 3 voltages right here. In this case, this is gonna be my A, B, and C. So my voltage A to B magnitude is equal to 138.56 volts, okay? Now, and again, this one, I'm gonna say this is coupled with this is coupled with that, and this is coupled with this. So I have primary, once again, delta, Y, I have 3 voltages, and I have 6 voltages that I need to deal with, and I have 3 voltages right here. So that's one, okay? The next question was, what if it's the other way around? What if the transformer is connected as a delta, delta Y, and the primary, again, hasn't changed, we'll have the same voltage on the primary. So B, I'm gonna say is delta, again, on the primary, on the high side. Oops. The high side. And then the secondary side, I'm gonna connect it as a Y. Yes.
Could you explain more which one's coupled to which one? Because I missed that part.
Oh, yeah.
Sorry.
So what I'm saying is, remember when I did those 3 little transformers? What I'm saying is, you can think of this winding right here, right? Is coupled with this winding. So if you look at it from this point of view, right? It's like this. I'm gonna do this, and this is a neutral.
Yeah.
A, B, and C, right?
Right.
So I have this winding like this,
And then the
right?
other side of the one.
And on the other side,
Right.
I have A and B. Do that make sense?
Yeah.
So I have those 3, so what I'm saying internally, the core looks like this. I'm gonna do it right here, so let me do it this way.
Yeah, it's like what you drew earlier. For the
Right, so you have the core, and you have A to neutral, and then you have A to B on that side. Make sense?
Mhm.
Okay, thank you. Forward side, where's my? Yeah, this is it. So, okay, so then I have same thing right here, same thing, the question you asked me, this is coupled, I'm gonna couple it with this I'm gonna couple with that, and this I'm gonna couple with that. Usually, by the way, when you're doing this, you have to be provided with that schematic. Remember that schematic that I was showing you like this? They have to write with the schematic because they can do it this way. They can shift the line. They can shift, or they can change the coupling, the phases of the transformer. But for the most part, 99% of the time is this. Because if you do not follow this, then you can have issues, right? But like I said, for now, let's just say that these are 3 windings that are coupled with each other. Delta on this side and Y on the other side. So the turns doesn't change, right? In 1 still 500 turns, in 2 still 50 turns, and then the voltage line to line still 2,400 volts on this side. And now A, B, and C, so 2,400 volts between this wire and this wire. There's no neutral, so we don't have to worry about line to neutral. So if that is the case, then we can go now to I'm gonna say this is the primary for now. Primary voltage. So we go to the secondary. So in this case, V2, same equation, is equal to V1 times N2 divided by N1, that doesn't change. In this case, we have V2 is equal to 2,400 volts times 50 over 500. That gives me 240 volts, okay? So, but remember, once again, this is my neutral, this is my A, this is my B, and this is my C wire. Actually, I'm gonna make it lowercase. C, okay? So again, I'm assuming that I'm applying across this wire 240 volts. Make sense? Okay? So I have 240 volts from line to neutral. So I'm gonna say here 240 volts. I'm gonna say this is my VB to neutral. Just magnitude. I'm not talking about phasors right here. Just purely magnitude. Okay, so if because I'm coupling this, I have 240 volts on the secondary, how do I get my voltages now from the line to line from VAB?
Root 3 times that.
Exactly. So I just take now the voltage on that winding on the secondary, right? Line to neutral, and I multiply by the square root of 3, and that's how I get my line to line voltage, right? So this is V2 line to neutral. This is V2 line to line. In this case, it's square root of 3 times 240 volts. That gives me 416 volts. Okay, so 416 once again is between the two lines A and B. 416. A very common voltage three-phase. I use this 240 right now, but a very common voltage three-phase is really 480, meaning the line to line voltage here. 480 is very common, which makes this voltage line to neutral 277. There used to be, not anymore, because I can bet you that the lighting here is probably not up to code, meaning what do they call those lighting? Fluorescent. You guys remember the fluorescent? You probably still have it at home, right? I have my home. I still have it because my home was built in I think it was 2000. The new code, I think, the new codes are asking for builders to use LEDs. But if you have a lot of fluorescent bulbs, they call it, lighting, is very common that those are 277 volts. That's the input of that lighting. Obviously, at home is 120, but you probably have one or two in your house, right? If you have any. Like I said, they're not that common anymore. Nowadays, I don't know. I really don't know. I used to be that, again, it was 480 three-phase and 277 this line to ground, and that's what they use for lighting. I don't know what other type of flows will use it now, but you will come across it. But that's a very common voltage. Any questions? So very simple, right? I mean, you're treating it just, the only thing you need to know once again is, hey, they're giving me the high side or the input side or the source side. First, they got to tell you how they're connected, and then they got to tell you the voltage. And when they give you the voltage, oh yes, one more thing I was gonna say. When they give you three-phase voltages, if anybody tells you, oh, this is a three-phase voltage and it's 12 kilovolts, 16 kilovolts, 4 kilovolts, it is always, they don't have to tell you, three-phase voltage is always line-to-line voltage. Okay? Whereas delta or Y. Actually, there was a student who told me they asked that question at Edison in an interview. So if I give you a three-phase voltage and I tell you the voltage is 12 kilovolts, is that line to line or is that line to neutral? They don't tell me otherwise. It's always line to line. Okay, don't forget that. All right, so I'm not going to get too much more into transformers, three-phase transformers. Let me see. see. I might come back to this problem. If not, I'll give you all the slides. Did I post it the last ones that I did? I don't think I did, right? You can check. What I'll do is if I didn't post it, I'm just gonna add the slides to the last one and give you a whole set of slides so that you have. There's a problem that we'll come back for another three-phase transformer, but I wanna get into the next topic. Okay, so we talked about transformer models and whether it's a three-phase or a single-phase. For most analysis, as we were discussing it before, you're always required to have a non-ideal transformer model, right? That you can put on your computer, whether it's low flow, short circuit, whatever the case might be. And we talk about the parameters of the transformer, and I also mentioned, oh yeah, by the way, we're really interested on the transformer impedance neglecting the magnetizing branch, but the magnetizing branch is still there, and in some cases you might still need it, right? So, and I said, hey, what if you have a transformer and somebody tells you, hey, I don't have any data on this transformer, I don't have any information for you to put on your software, and you got to determine what your transformer equivalent impedance is, so you can then perform what we call a transformer short circuit and open circuit test to determine the transformer parameters. On transformers, by the way, it is very simple. All you need is a variable voltage source, right? Like what do they call that? There's a name for it.
Power supply.
Power supply, but the variable ones have a name. I always forget the name. The ones that you can give from 0 to whatever.
Switching regulator?
Something like that. I can't remember. There's a name for those. And we have them in the lab. This is the only lab that I wish we will do. You know what? For those of you coming to class next semester, maybe that actually, you know what, Maria, we have like 3 more. Remember I said that we're going to do. Maybe I saw a transformer there. Maybe we'll do that. I won't ask you guys to do it, but I'll do it for everybody to do it. But all you need really is a source and a multimeter. That's all you need to come up with to find the transformer parameters. So if you have, once again, transformer primary and a secondary winding, like this. I have a source right here connected to the transformer, a variable source. A variable source, okay. And there with the source, and the source can be either on the primary or the secondary side of the transformer. It doesn't really matter whether you have it on the high or on the low. You just gotta have source on one side. So the first test, which is what we call the short circuit test, basically what you're doing, you're shorting the secondary side of the transformer, okay? And then you start increasing your voltage, right? And then you take the necessary measurements. So we'll talk about the necessary measurements. The second is, so this one is really an ammeter right here. And ammeters are a very low impedance, right? So the current just basically goes through it. So that's your short circuit test, okay? Similarly, you take the same thing, same transformer, with a source. I'm going to put it on this side. Again, variable source. And the second connection, same thing, except that in this case, I do what I call an open circuit test. So what I do is I have a voltage measurement across it, so an open circuit. The voltmeter happens to have a very, very high impedance, so for all practical purposes, when you put it across, it looks like an open circuit, right? And there's a low impedance, looks like a short circuit. Okay, so that's the idea. So let me start with the short circuit test connection. Short circuit test.
Does the top one say SC or S
Short circuit, open circuit.
on the ammeter? Is that an S what?
Short, I'm sorry.
Oh.
Short circuit, and you can say this is open circuit test. Okay. All right. So let's we say that the test, I'm talking about a short circuit test, is also known as the impedance Cooper test. That's a name, but that's what they call it in some places, and they're referring to the same thing. And as I said, the test can be performed on secondary or primary, it doesn't matter. Whatever you have access to. Meaning, I can move the source right here and I can short this winding, or I can move the source to this side and open this winding, or vice versa. It doesn't really matter which side you short and which side you put the source. And then the setup, here's my voltage source, variable voltage source, again, right here. And then I'm going to have this right here. Like this. This is just an internal, but you don't really have to do it in the lab. It's all set up for you. All you gotta do is the connections, but we do have this. And this is gonna be my voltage meter, and this is gonna be my current, my amp meter. And here, the whole thing is a multimeter, and it measures amps, volts, and power. I'm gonna call S for now, okay? So this is a multimeter. So on this side, what we're gonna do here is the transformer. Okay, so again, source right here, meter right here, and then the transformer itself right here. And then I'm gonna take this side right here, the secondary, because I'm doing it secondary, and I'm just gonna short these terminals right here for the transformer. So this, once again, this is the primary. On the high side, give me the low side, doesn't really matter. All I do is on the side of the transformer there's no source, I connect the two terminals together like that, just short them out. Okay? Basically what it's the same thing, same concept that I was explaining there, but that's what it's gonna, that's just gonna track that term right here. So what do I measure? I'm gonna call this BZ for the short circuit test. This is the input power out of the multimeter. VZ is the applied voltage. And then last but not least is your IZ, or your input current. Okay? All right, so the goal is the following. IZ is equal to I rated. Let me explain this. VZ should be between 2% and 12% of the V rated. And then PZ is just your measure watts. Okay. So what am I doing on the first test? Short circuit test. And I'm gonna go back to because we do something similar on the induction machines. We did induction machines, Maria, and synchronous machine already parameters, so we just did, can't remember which one we did. We did both.
Synchronous machine?
Synchronous
Yeah.
machines, right? So it's a very similar setup, and all you do on the first one is you take the source, and that's why you gotta have a variable source, and you start increasing the voltage, right? And if things are good for you, when, say the transformer is rated for 120 volts, that's the rating of the transformer secondary, of the primary, I'm sorry. You don't have to get the voltage here where the short circuit says all the way up to 120 volts. If you get it between 2 and 12%, that's good enough to push current through here, okay? So, but what you're trying to really get, I see to be, is the rated current. So you start increasing the voltage, increasing the voltage, increasing the voltage, until the current that you measure here is the transformer rated current. Do I make sense, everybody? You start increasing the voltage, you bump it up, bump it up, bump it up, and you measure, you're just looking at the current, you know what the rated current of the transformer should be, right? That's given. But once you get to that rated current, then you stop. And hopefully the voltage was between 2 and 12%. Can it be a little higher? Sure, it can be a little higher. What cannot be higher is the current, because then you damage the transformer.
You're talking about a DC load, right? So
No, AC.
Oh, I see.
AC, otherwise, if I put a DC, then I don't have transformation. Remember, I can, if I don't have a
Yeah,
variable.
That's why I was confused, I was unsure about.
Yeah, it has to be AC. So your source must be AC. So, once again, basically what you're trying to get is the transformer you're trying to push rated current through the transformer, right? With this source, but because you don't have a load right here, you don't have to take it all the way to its rated voltage. If you do, then that current gets really, really large. You can damage the transformer winding.
It's because the transformer itself acts as a load, right?
Exactly. The transformer is acting as a load. And I'm sorry, Maria, I keep on picking you, but remember when we were doing it in the lab, and then we give you a number, we said, you can increase the voltage, but don't exceed this current. That's the rated current in that case of the winding of the machine. Similarly for the transformer, because the machine is acting as the load. You're right. That's a very good way to see it. Make sense? So you take those measurements. All right, now you have that. Then we use those measurements as follows. Okay? Erase the computer. So, here's something that we deal in the lab, and we always talk about it. We're going to neglect the losses of the instrumentation. Hopefully this box right here, it's as good as it can be, so that we don't, but you still will have some losses, very small losses that will reflect on your transformer parameters. But let's assume that you have some really good instrumentation. So then we have this RE, which is equal to, using these values, PZ divided by IZ squared, and that gives me a value in ohms, okay? Z is equal to R plus JX. You remember that from the transformer, right? Your primary, secondary resistance, so your combined, what we call the R equivalent, EX equivalent, and Z equivalent of a transformer. So this right here happens to be ZEQ. So Z EQ magnitude, by the way, is equal to VZ, meaning the measurement that we took from the meters, divided by IZ, and this gives me a value in ohms. So, from the measurements that I'm taking here with the setup, I can compute the resistance and the impedance magnitude. What I cannot do, I cannot compute this value. That I cannot compute. I mean, I cannot compute that meaning with the measurements that I'm given because I'm using real losses, right? So that reflects into the resistance. But one thing that you know is the following. You know this formula, right? So you can solve, if you know this value, and you know this value, you can solve for this value. So what we say is that XE is equal to, the square root of Z squared, ZE squared minus magnitude, of course, right? It's going to become a magnitude regardless. Minus RE squared. So that gives me that gives me the XE. So I can use then this value that I measured, this value that I measured to compute this value. So basically what I have is E, which is equal to RE plus JXE. Okay, so all I do is I add the imaginary, right? That's the imaginary part of your impedance. Now, what does that represent now? Okay, you remember this? So I'm doing this on the primary side of the transformer.
That's the phase, right?
Say that again?
That's the phase of whatever the impedance causes to the input, right?
That's what I'm saying?
The phase that the transformer as a load causes.
Right, exactly. So what I'm doing here then, with this, I'm have the ability to do this. Remember, I'm doing the testing on taking the measurements on this side of the transformer, right? So this becomes then my RE, I'm gonna call it right here, because that's what it's called in the book. And then XE, okay? This, in reality, is what, maybe I mentioned this is what the transformers manufacturers will give you. That's what they call the transformer liquid, or they call it reactants. I don't tell what the name comes from, but this is the copper losses of the transformer that they're giving you right here. So you can say, oh, I want this model. Let me ask this question really quick as we talk about this. Okay, so this is R1 plus R2 prime, right? Is the total, okay? This is X1, JX1 plus JX2 prime. Oh, okay, so it's basically what I just got is the transformer equivalent circuit as seen from the primary or high side. I'm going to assume that this is the high side of the transformer. Okay? So if for whatever reason you say, well, the model that I want to use, I want to do this, R1, JX1, R2, and JX2. Remember I told you this before, I said, oh, you can take this value divided by 2, and then use the 1 over a squared and transfer that to the other side.
To get both sides.
And then you get both sides, right? Once again, the manufacturer of the transformer, that's what they did. That's the test that they performed to give you this model for the transformer equivalent impedance or transformer model. Now, what is the difference between the values that you get and the values that you get from manufacturing? most likely the manufacturer will give you very, very accurate numbers. And the reason because they have very, very nice, I'm gonna say very expensive instrumentation, well calibrated. Yes, sir.
So those numbers that they give you or that you find, that's at a rated frequency. So if you were to change the frequency, then
Oh, then that's a whole different
okay,
deal.
got it.
That's a whole different deal. Now, but you can do that, right? Remember that's a very good question. So say, what he's saying is, well, this information that I've been given is all assuming that this was done at a 60 hertz frequency, right? If I apply a source that has a different frequency, not 60 hertz, say for instance, you have a source that is 120 hertz instead, that's gonna affect this value, but it's not gonna affect this value. Your real losses are your real losses, right? It's not affected because this value right here, remember, X is equal to J omega L. So as you increase the frequency, what does it increase? The reactance increases, right? So it's a frequency dependent, but we're assuming that the source is perfect. Now, do you see now? I mean, but looking at transformer, do you see how the transformer when it's dealing with harmonics? It's not the same when the transformer is dealing with a perfect source or load, I'm sorry, which is 60 hertz passive load. Once you have active loads, the current, you're gonna have currents flowing here at different frequencies. It is going to affect your reactance. Your reactance is not necessarily fixed, but that's a bigger issue. That's more for power quality type analysis that you'll have to do. But does that make sense? It's a very, very simple test. Really, it is. It's not rocket science. I think the key of this is how accurate this is. And in the lab, we have that problem. I mean, we have some meters, like people will come and say, my numbers, oh, wow, those numbers are really off. Oftentimes it's the instrumentation, right? Or they're really off, by the way. And half of them, one pays worse, the other doesn't work. So the internal impedances of the instrumentation and the accuracy, they've probably never been calibrated, makes a difference. Does it make gross differences? No. Good enough for a model steady state analysis. But if you don't have it, you can do that. This one is actually very simple. Machines are a little more tricky to do. Transformers are not. As I said, all you need is a variable source. That's all you need right here. And a good multimeter. And then you can come up with the transformer parameters. By the way, for any type of transformer, whether it's a small transformer or a very large transformer. Okay. Any questions? All right. So that's the short circuit test. The next is what we call the open circuit test. So the short circuit test, let me see if I have one example, long example. Okay, so the short circuit test once again gave me that the transformer primary and secondary losses. What do you think is the open circuit test going to give us? What are we missing on that transformer model? Assuming that we wanted a complete model. As a matter of fact, I'm going to say 95% of the analysis that you'll do, that's all you need. But what are we missing? We're missing one branch.
The flux.
The excitation branch, right? Remember? So we have a branch that is here. Remember? So to analyze it, to get the parameters for the excitation branch, that's when we use the open circuit test.
What do you mean excitation branch?
Remember when I talked about the transformers and I was saying you have this is the non-ideal transformer model, complete model. Remember I talked about it? We did a couple of examples and I called this R1, remember JX1, R2, JX2, and then I told you, oh, there's another branch right here called RC and XM. You remember that?
I don't think I was here, but.
I remember I said, and I did an example, and I told you guys, 99% of the time, we neglect the magnetizing branch. Remember we talked about that? Because these impedances are really, 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 really high in comparison to that. So most of the current, you want it to go here to here, and you want very little current right here. When do you need this? Is when you're doing some sort of transient analysis. But that it still exists, right? That's the magnetization branch. Did I say that or no?
Yes, you
everybody?
did, you did.
I did talk about it, right? I hope I did. I'm sorry if I confuse you. All right, so the open circuit test. Open circuit test. Okay, so what do we do here? This is also known in the industry, of course, as your core losses. Okay? Okay, so the setup, same thing. You have a voltage source right here, variable voltage source. Let's say V, so we don't get confused that it's current. Then I have again my multimeter. Multimeter like this, and this is voltage, and this is current, amps, and this box right here is the multimeter. This is source again, and then my transformer, and I'm going to connect my transformer right here. So I'm using the same side or the primary side, I'm going to say whichever transformer. And then I'm going to leave this here open, okay? So, on this one, let me see. I'm gonna call the, as I perform the test, I have these measurements that I need to take. I'm gonna call the I that I'm measuring. I'm gonna call the IEXC or excitation. And the excitation current should be between 3% to 10% of the rated current. In other words, you what you're trying to achieve is to get the current that this ammeter sees to be between 3 and 10% of what it's rated for. Okay? So if the transformer is rated for 10 amps, right? All you need to do is to get this value to be between 3% and 10% of the 10 amps. That's all you're trying to achieve. Okay, so in this case, VEXC or excitation voltage is equal to V rated. Okay, so you have control of that again. And then the power that you measure is what we call the PEXC or the excitation power. Okay, so that's what you're gonna measure PEXC, IEXC, and VEXC. So in this case, you have the variable voltage source, you're gonna start increasing your voltage until you get this voltage to be whatever the transformer voltage is rated for. Say the transformer is rated for 120 volts. You are gonna get this all the way to 120, and then you're gonna measure this current, and hopefully it will be between 3 and 10%. And you should hit it. Okay, you should hit the value, so you should be between that. Obviously, you don't want to go higher than that because then you're going to have other issues. So, and in the lab, because as I mentioned to you, things are not perfect, right? Especially the instrumentation we have. Sometimes we have to just get to the edge and maybe not even cross the edge, right? And we have that even with the machines, right? I mean, when we do the what we call open circuit on the machine, is when we have the, when we get the machine into a standstill, right? So the machine is locked. We put a load, a heavy load on the shaft. Sometimes the load is not good, it's not high enough to get it to that value that we get rated sometimes, and the machine will start moving, right? But we can still assume that is standstill. Similarly on the transformer, point I'm trying to make is I'm gonna raise the voltage all the way to this rated value. Say for instance, instead of 3 to 10%, I get 11%, that's fine, it's good enough. What I don't want here is to get too rated, otherwise I can damage the transformer itself. Do I make sense, everybody? But all you gotta do is you follow the steps. Okay, so with that, then we can compute our magnetizing, or M. I'm gonna call this, well, I'll come back to it. Rm. So Rm is equal to P excitation, or the power watts that we measured here, divided by the I excitation squared, and this is in ohms. And then Zm, which is the magnetizing branch impedance, which is VEXC divided by IEXC, and this is also in ohms. So again, we know for the magnetizing branch, this branch right here, this being Rm, and this is X, what do we call XM? Okay, it's a series branch. Okay, so I can measure this using the I can compute that. I'm sorry, using the measurements that I took. I can compute this using, but I cannot compute this, just like what we did on the copper losses, right? So same thing. We say that XM is equal to Zm squared minus Rm squared. And that gives us this value and this value. And the only thing we know that this is the imaginary part, right? So this gives us, let me redraw this thing here so that we have a complete mark. I did it on this side of the transformer, so I'm going to have it like this. Okay. So this is REJXE. This is RMJXM. Okay? Does that make sense, everybody? So, again, I can put the source on this side and get this parameters, or I can put the source on this side and have these parameters computed right here, right? And if I did everything right, the numbers should come up. And if I want to transfer, I can, if I want to put half on this side and half on this side, just divide by 2 and transfer using the equations that we have, using the turns ratio, right? X2 prime is equal to a squared times x2, right? Remember those formulas? That's all you need to do. So the magnetizing branch, as I say, you can also put this as a parallel branch, but the results that we get is the series branch. You can convert that to a parallel one, but as I said, 95%, if not 95% of the time, when you do an analysis, you don't have to consider that. And the problems even on the homework, I think, and on the test, I won't ask you for magnetizing branch. If I give you a problem to do it, I give you values, then you have to come up with it. But what I'm saying is, for steady state analysis, that's not required. You can ignore or you can neglect the excitation branch. Okay, any questions? All right, I think I do have an example. Maybe I can recreate that example for the lab because we do have a couple of open spots on things we can do. So, example, 10 kVA transformer, 480 on the primary, 120 volts on the secondary, AC of course, single phase, short and open circuit test is performed. And we have the following results. So test V, I, V. Okay. I say open circuit and last short circuit. So here I get 120 volts for the open circuit test. I get 2.5 amps, and then I get 60 watts measurements. So remember, these are my EXC or excitation. For the short circuit test, I get all the way to 26 volts on this test. The 26 volt gave me 20.83 amps. Okay, and I got 200 watts of losses. And once again, this is your E, right? E. So that's my V excitation, I excitation, P excitation. This is my VE, PIE, and PE. So those are the values that I get when I perform this test. So with that information, I can then do the following. I'm going to say determine the leakage impedance referred to the primary of the transformer. Let me see. So I'm going to do this because I have that information. So I know that the I on the high side is equal to magnitude S divided by V rated. This is a single phase transformer. So I know that this is the 10 kVA or 10,000 volt ampere transformer, and my V rated on the, I'm going to say on the high side, 480 volts. So the rated current on the high side is about 20.83 amperes. I'm going to say that. Okay, so that's a computation that I can make right at the get-go. My RE from this measurements now, my RE is equal to PZ divided by IZ. Again, I
Squared, right?
EX, yeah, square, I'm sorry. So this is 200 watts divided by 20.83 amps squared. So RE is equal to 0.46 ohms. Okay. My ZE is equal to the voltage. In this case, the voltage is 26 volts divided by IZ, which is 20.83 amps. And that gives me value of 1.25 ohms right here. So therefore, I can say that XE is equal to the square root of 1.25 squared minus 0.46 squared, and therefore XE is equal to 1. I'm going to put a J, J 1.16 ohms. Okay, so with that information, basically what I have is my transformer my transformer impedance ZE is equal to 0.4, what did I say, 0.46, 6 plus J 1.16 ohms, okay? So that's that. Next is my ZM, or magnetizing branch, and I'm gonna do this on the low side. So S is equal to VEXC divided by IEXC. So in this case, I got 120 volts divided by 2.5 amps, right? 120 volts divided by 2.5 amps. That gives me a ZM on the low side of about 48 ohms. So it's pretty high, right? In comparison to this, right? And then my RM, or the resistance of magnetizing, is equal to PEXC divided by IEXC squared. That gives me 60 watts, divided by 2.5 amps squared. And that gives me an RM, the low side, of 9.6 ohms. Okay. Hence my Z, my XM, What am I saying? Z. I'm going to use those formulas. Let's see. So XM on the low side is equal to 48 squared minus 9.6 squared. That gives me an XM of 47.08 ohms. Okay, so I'm going to transfer this to the high side. Z M high is equal to A squared times Z M low. So this is going to be ZM high is equal to the transfer ratio, which in this case is 480 divided by 120 squared, one that we already used, times 9.6 plus J 47 ohms, and that gives me a ZM of 153.6 plus J 756.8 ohms. Okay, so now I have the equivalent, and as I said, the magnetizing branch, as I told you guys, 95% of the time you're not going to need it, because you're not going to have what you really need to do most of your steady state analysis computation is this. So this, for all practical purposes, I'm going to draw it right here. I'm going to ignore the magnetizing branch. Basically what we have is this now. Okay, so this was 0.46 ohms, J 1.16 ohms. Okay, so what will you do if I'm asking you to give me this? And I don't tell you anything else or any other information while I'm doing it first. R1 JX1 R2 AX2. Forget about the magnetization brine for a second. So I'm giving you this right here, right? Exactly. So I take 0.46, you divide it by 2, right? So that's 0.23. So you leave 0.23 on this side, and what do you do to bring it to the other 0.23 to the other side? What do you multiply by?
Number of turns?
I'm sorry, yeah, but
The ratio.
remember the formula? It was 1 over a squared times, you remember the formula?
Times the,
If I'm transferring from this side to that side, I multiply. Say for instance, if I want to take R2 and I want to make it R2 prime, I'm going to say R2 times a squared. And then I put the value right here. You remember that?
so 1 over 8.
You guys don't remember that? Really?
I wasn't here for that.
Oh, you were not here. I'm sorry. I was like, man, did I talk about that? Yes, you remember that, right?
Yes.
No,
Yes.
Okay. Yeah,
Yes,
sorry.
yes,
I was
yes.
like,
No.
Stop. So, anyways, now remember the other way around. If in this case you're giving this values, and I'm saying I want you to build me. This is R. I'm gonna call it the way I wrote it on the lecture. REQ JXEQ. It's the same thing. What I'm telling you is this: I want you to take this transformer model and give me this transformer model where I have primary and secondary separated from each other. And I said, if they don't tell you anything, all you do is you divide this value by 2, right? That becomes, in this case, will be R1 will be 0.46 divided by 2, that's 0.23. Did I do this right? Okay? Oh, that's R1. How do I get R2? Oh, R2 will be equal to 1 over a squared times r, in this case, 0.23. That will be the value that I put on this side, right? You remember that?
Yeah.
Yes.
I'm just curious, a squared, is that just, where do you get that value?
Oh, a squared. A is equal to n1 over n2.
Oh,
In this case was 480 divided by what? 120. So that's what we call the turns ratio of the transformer, right? So when I transfer, look at this, when I transfer stuff from this side to that side to get that equivalent,
You multiply
all
that.
I do is I multiply whatever value I'm given here by the square of this. If I want to transfer from this side to the other side, then I do the opposite. 1 over a squared. This is 1 over a squared times, in this case, will be our half of, 1/2 of R1, right? In other words, I divide this into 2 resistors. I leave 1/2 on this side, 0.23, and I move the other half to the other side. But when I move it to the other side, I have to multiply it by the inverse of the turns ratio square. Yes, sir?
So one more question on
Yes.
top of that. So if the high side and low side swap positions, then you flip the relationship, right?
Exactly.
Okay,
Exactly. As a matter of fact, you can perform the same test
backwards,
backwards,
Yeah.
and the numbers are gonna come,
exactly the same.
and it should come back the same, right? Because you're measuring the same, the same windings, right? As a combination, but how do you represent it mathematically, right? Or how you get the values from the measurements matter. Yes, sir.
For the copper short circuit test, you use the high side.
Say that again.
For the copper short circuit test, you use the high side.
It doesn't matter. I can use the high side and then transfer it.
That means for the excitation branch, I can use the high side to begin with, so I don't have to do the conversion.
That is correct. That is correct. So the only thing that I talk about, I talk a little bit about this. For the most part, transformer models are gonna be on this side, on the primary side, and the excitation branch more like it will be here, right? But since as I said, we're gonna ignore it. Let me say this because I don't want you to think that this is this right here is non-important. This is important, but when is it important? If you're doing, if you're energizing transformers, right, for the first time, well, not the first time, after they have been de-energized for some time, this branch right here becomes critical. Because usually when you energize the transformer, this right here, there's no load. So it's an open circuit, right? So that's when the excitation branch comes in place. Why is that important? And as a matter of fact, this magnetizing branch right here, the way it performs is what we call the excitation current. It can actually confuse relays, and that's the problem because the protection, obviously there is no load, but you close it, and then there's this current with high content of harmonics, because it's part of the magnetizing branch. Is when you're starting to shape that hysteresis, you take the transformer into the saturation point, and then sometimes relays will get confused and will trip, right? So that's mostly for protection engineers, and that's what they want to know what this excitation current is. But once you get the transformer running in steady state, there is very little current. I'm going to put the excitation branch right here. There's, again, this is all based on your transformer design. Here's my excitation branch again, RM, JXM. You want all the current from the primary, I1, to go and be transferred to I2 on the other side. You want very little current on the excitation branch flow, and that's what this is, a very high impedance there. But this also depends on the design of the transformer. Remember when I was talking to you about how this is really what this is capturing is the flux leakage. Remember we talked about it when you have the flux lines and the lines of flux, the ones that don't stay inside the core and they escape to air is what makes this, right? So the better design you have, the higher that branches, the more current from the primary gets reflected on the secondary, and hopefully, as I said, if you did a really good design, very, 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 very tiny amounts of current will flow through that magnetizing branch. And that's what we tend to ignore it and say, no, we lose it, say analysis, don't worry about it. But there is places where that is required. Any questions? Let's see.
One question.
Yes, sir.
How would you do the high side one for the excitation part?
How would I do the?
So I always have to do the low side, but I don't know what that means, the L. Can I do the H just like how you did it on the short circuit?
You get what you're saying is can I put the source right here and short and open the side? Is that what you're saying?
No, I mean, you see I high side.
Yeah.
So the excitation plan is always EM low side.
It doesn't matter. You can transfer. Remember I transferred from the low side to the high side by multiplying by the A squared, the trans ratio.
But the excitation, the open circuit test always start on the low side.
Oh, no, it doesn't matter.
Okay,
So if you flip it, obviously the measurements, the currents and the current and the voltages will not be the same because you're on the other side of the transformer, but when you apply it to the formula, you should get the right values.
Okay.
You see what I'm saying?
I see what you're saying, but you didn't quite get my question. So for the value that you're giving us, that's for the low side value, right? For the open circuit, is that the low side value or is that high?
That was the low and I transferred to the high.
You already transferred to the high.
Yeah, I did it at the end.
Oh, at the end, yes, but this is the low side.
That is correct.
Okay.
That is
You
correct.
answered my question.
That is correct. So you can do it at either side. Like the values, once again,
So how do I know that is a low side or a high side?
how do you know how do I know it's because first of all, it's the rated voltage that got achieved as 120.
Okay.
The high side was
Okay, so that
480.
determined, because if it's 480, that's another story.
Right.
Okay.
Let me do this, okay? I think I saw another problem no, let me see, I think I saw another problem. Where they do the measurements on the high and the low, let me do a problem like that, but it should come up with the same value. Obviously, if I'm doing on the other side, I'm taking this to 480 volts, that's gonna have a
Change
different,
that.
right? The losses are gonna be the same,
But
because the losses,
that's
but
how
this
you-
current is gonna make a
So
difference.
that's how you determine if the high side and low side. Vice versa, for the short circuit, you have 26 volt and you say it's around 3 to 10% of
That's
the
right.
rated voltage, so you can, like that, you would know if it's a high side that you given to us or if it's a low side.
Exactly,
Okay, got it.
exactly. And it also depends on where you place your measurement devices, right? I mean, if you're doing it, all you gotta do is follow it, okay? As I said, let me see if I can find a problem for the both sides, and we should come up with the same values. Let's see. I have 916, let me see. Oh, man, this is a long problem. Wow. Let me see if I have a short problem. Okay. Let me do this, okay? Because both problems are really long, and it's 916. I don't wanna make it halfway, so I'm gonna do this. I'm going to post the slides, okay, with one more problem. I'll give you the homework. I think it's 3 problems, transformer problems, and I won't test you on this, by the way. I won't, on the test, you will not have a problem like this. But you will have the problems where I give you the primary, I want you to transfer the secondary, and I want you to put a load, we did a couple of those exercises. So I want you to go through the homework problem, and then before the exam, I'll review those homework problems, okay? The only thing, no, I already talked about it, so you should be able to get the homework, because I wanna get into the induction machines, next week, okay? So I'll post it, go work on them. Oh, yes, this is what I was gonna say. How about, my recommendation would be not to leave this homework problems to the very end, because they don't actually be cramming on transformers, induction machines, and synchronous machine also at once. They're very similar, by the way. I mean, in concept on how the circuits, especially the induction machine and the transformer, reason why we talk, we call, some people call induction machines moving transformers, because it's a very, very similar. When we get to it, we'll see how we deal with the secondary side of or the rotating winding. No big deal, we'll go through that. So, but I want you to work on the homework problems right off the bat, so that you don't cram it at the end. Because like the first test was easy because it was kind of the same thing, this one is not necessary. So if you leave it at the end, it's gonna be hard, then if you have questions about the homework, you can come back and ask me those questions. I'll post the slides, I'm gonna combine them, and then if you have any questions, let me know, and then next week, we'll work on on induction machines, that's what we're gonna do next. So hopefully it'll take us about 2 lectures, and if it takes us more than that, if I need more time, I'm not gonna ask you to come to class, an extra class, what I'll do is I'll record, just to make sure that I complete all the material, okay? If you have any questions, I'm still here, remember what I told you at the beginning, so just let me know if you're interested, I can discuss it with you. So, other than that, thank you, everybody. Have a wonderful, rest of the week.